Hello, everyone. Welcome. So we're very happy to have John McCammond here today, who will tell us about repetition and insight, roots, ratios, and Ramanujan. And how would you like people to ask questions?
All right. All right. Shall we get going?
How do you want them to ask questions? Should they type in the chat or unmute themselves and talk, or what do you prefer?
Let's see. Yeah, let's talk about mechanics. So first off, I guess one thing you guys should know is that you should make it so that I'm visible on your screen because I'm somebody who likes to talk with my hands. And so there'll be places in the talk where you'll need to see my gestures. The other thing is that I would love it if I could see a few of your faces because that really helps me gauge whether people are understanding. Great. Okay, so I see a couple people with their cameras on. So yeah, so during the talk, if you raise your hand, you get bumped to the top of the list. I can see that you've got a question, and then I can go ahead and answer. We can do it that way. All right, sound good?
Yep.
Great. Okay. Anything else on the administrative notes, Simon, before we get started?
No, I think that's fine.
Okay, great. All right. So this is a talk about repetition and insight. It's going to be about these three topics about iterated square roots, iterated continued fractions, and also about Ramanujan. The story is really going to start back with Bill Thurston. And so Bill Thurston is a topologist. I'm a topologist. I should say sort of at the beginning that the talk is going to be about stuff that's not really related to the things that I normally do as a mathematician. I'm a geometric group theorist. I do things with polytopes and topologies and groups, reflection groups, etc. But this is going to be about something that I got interested in and investigated back 20, 30 years ago, and I've been giving it as a math club talk because it's a lot of fun. And maybe at some point I'll write it up as an article, but currently it's just slides. So the story goes all the way back to 1999. I was a brand new, relatively new PhD. I was going to the Cornell Topology Fest for the first time. Bill Thurston is a big name in the field. He was doing all kinds of amazing things. I was really excited to see him. And when it finally came time for me to be able to meet this amazing mathematician and see what he was doing, what he did was sort of surprising to me. He got up in front of the audience, and he had this new software that he developed. And what it was doing doesn't really matter. It was something about finding the volume of hyperbolic three manifolds, drilling out a geodesic, putting it in a different way, and recalculating volume. But the thing that I took from this was that here's somebody that I had a lot of respect for. I really enjoyed his articles. And he got up on stage, he loaded up his software, and he was showing us what it was doing. And there was this number calculating volume. And he had a button that would drill out a geodesic and then put it in a different way and recalculate volume. And what he did next was he said, look what happens when I do this. And he just kept, and so hopefully you could see my hand gestures. He just pushed the button repeatedly. And then it was like, this is something I used to do in high school on calculators. You know, I would like have a handheld calculator. You guys don't have handheld calculators anymore, but I had a handheld calculator. I'd type in a number, and then it was like, oh, I can push the cosine key repeatedly. And oh, look, the number's converging to something. Oh, that's interesting. And then you go and you try and figure out why. And so most of his talk was about why the numbers on the screen were converging to some number. But the thing I took from it is that, many of us have slightly autistic tendencies. We want to do things and we select, yeah, let's go ahead and just try and see what happens if we do this repeatedly. And often when you do things repeatedly, interesting things happen. And then you go and you try and figure out why interesting things happen. And then once you've figured out why, that leads to some insight, some deeper insight. And I see there's a question in the chat. Nope. That's just, okay. All right. So anyway, so this is all about what happens when you do things repeatedly. All right. And then try and figure out what's going on. So I want to start with the calculator question. Like I said, I don't think you guys have handheld calculators anymore. You probably never did this in your time, but you could do something like, okay, type in a number and just hit the sign key repeatedly. And if you do that, you do that, you get 0. So that one's not terribly interesting. Okay. But what if you do it with cosine? If you do it with cosine, you end up getting this number. No matter what number you start with, if you start pushing the cosine key repeatedly, you get this number. Or at least you do, unless you're in radian mode. And then you get a different number. And so hopefully at this point, you start thinking, okay, well, what in the world? What is this number? Where is it coming from? What's going on? And so what I want to do is I want to give you a quick picture. And so let's go ahead and draw the picture. And hopefully you guys can see my cursor. And so imagine that I took a number and like this number, and I plugged it in. Let's do this number like here. If I took this number here and I plugged it into the cosine, then I would go up to the curve. And then that gives me this value. But then once I have this value, I want to plug it into the cosine curve again. And so to plug it into the cosine curve, I have to get it from the y-axis back to the x-axis. So I can go to the curve y equals x and then back down. And now I've got it as, change it from, so I'm going from an x value up to the cosine curve, over to a y value, over to the y equals x curve, back down to the x-axis, so that I can then plug it in again. But you can see that as I'm doing this, going back to the axes doesn't really do much for me because I'm coming over to the y-axis, but then going over to the y equals x curve. And so what happens is that I'm going up to the cosine curve, going over to the xy curve, going up to the cosine curve, going over to the xy curve, and I end up spiraling into the crossing point. And so that's why the answer is always coming out to being the same answer, is that no matter what I start with, I start spiraling in towards the unique place where y equals x crosses the curve y equals cosine x. And if I was doing this in radian mode rather than degree mode, then the curve, the cosine curve, would be stretched out and I would get a slightly different answer. So far, so good? Okay. All right. Let's now talk about some other repetitions that are sort of give a bit more of the flavor, the kind of thing that I want to talk about. So imagine that you said, you had a question, you said, okay, well, x to the 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 x dot 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 is supposed to be equal to 2. What's x? And first off, you have to figure out, okay, well, what do I mean by this? I probably mean with the parentheses, so that x to the parentheses tower of x's, because if I did it the other way, then it's not going to work out the same way. But it's not too hard to see that if there is an answer, the only possible answer has to be x squared equals 2. Because the entire exponent looks like the whole thing. There's sort of a similarity going on. And because of the similarity, we have to have x squared equals 2. And so the only possible answers are going to be plus or minus square root 2. In fact, x equals negative square root 2 is very questionable because I don't know if you've ever thought about such strange things, but you've probably never seen a definition for negative square root 2 raised to the negative square root 2. And there's a good reason, because we usually leave this completely undefined. This is not something we ever want to talk about, and partly because if you ever have a negative in the bottom part of a exponent like this, then strange things can happen. And here's one that you can think about a little bit later. If you start with -1, you could think about it as the cube root of -1. You could think about it as -1 to the 1/3. You could think about -1 to the 2/3, 2/6. You know, if you could just think about, oh yeah, Mari.
My question is that we concluded via using like self-similarity here that we get the equation like x squared equals 2, and so
Yep.
if we do this sort of infinite power tower thing, root
Yeah.
2 to the root 2, we get 2. But if we did this x to the x to the x to the x equals 4, couldn't we get the same answer?
It's one of the, so we should be a little careful about what I'm saying about with the plus or minus 2, or the x squared equals 2. What I'm saying is that if it has an answer, the only possibilities are going to be root 2 and minus root 2. And so if you did the thing where it's equal to 4, then it would be like, okay, and then you try and do it. It's like, okay, well, the only possible answers are plus and minus 2. And in that case, you would end up going and saying, oh, you know what? Actually, neither of those work. Therefore, there is no answer. All right. Cool. All right. So the thing I want to show here is just that we're going to rule out the minus square root 2 right away, because minus square root 2, we never want to talk about negative bases to irrational exponents, because even with rational exponents, negative bases are sort of a little bit tricky. And if you just take a look at this list, something went wrong as we go from the left side to the right side.
Wait, but can we also say x to the 4 equals 2 because of also self-similarity again?
Sorry, say that again?
Did we say x to the 4th power equals 2 also, or?
Oh, right, it's x to the 4th. Yeah, it would be 4th root of 2.
Why are we not allowed to do that?
You might be able to, yeah. But
so there's no answer at all?
Let's see. So I haven't thought about it. So let's go ahead and just talk through it. So yeah, so if you have the tower equals 4, then it'd be like x to the 4th equals 2 because of the similarity. So the only possibilities are going to be 4th roots of 2. And then at that point, we're going to rule out the negative because negatives just really don't work in these kind of towers. And then I think at that point, like I say down here at the bottom of this slide, this means that, here we think that x equals square root of 2 would be the only possible solution. In the case that you're talking about, we'd have the 4th root of 2 being the only possible solution. But then at that point, we'd have to actually do some work to see whether that makes sense. Typically, when you start looking at 4th root of 2 to the 4th root of 2 to the 4th root of 2, I think that what happens in that case is you end up proving that as you do the 4th roots, you end up getting an increasing sequence. It ends up being monotonic and bounded, and then it's approaching, and you could say, yeah, it actually works.
Wait, when the tower is equal to 4, it should be x to the power 4 equals 4.
Yep.
So then the solution would be root 2.
Yeah, you guys are pushing me to think about things that I haven't thought about. But basically, the main lesson that I want us to think about, so this is good. Go ahead and keep thinking about it. But the thing that I want us to take from this is that we can very quickly limit ourselves to there's only 1 or 2 possibilities. And then at that point, we have to actually do some work. All right. So, yeah. So whether it actually works out with different numbers, I'd have to think about it, and I'd have to actually do the work. But I think that very quickly from the structure of the problem, you can get down to knowing that there's only a couple possible answers. And in some cases, there might be no answer, and in some cases, there'll be a unique answer. All right. I'm going to get to some pretty pictures later, so I'm going to keep going. All right. So let me do this is sort of a little interlude. This is sometimes called freshman addition, where you add fractions the way we all wish fractions were added. Where, if you have a over b plus c over d, it would be great if adding fractions like this could just give us a plus c over b plus d. But of course, that's not the way we add fractions. But what if that was? What if we did have that operation? Let's put a little circle around it just to say it's going to be a new operation. Let's investigate what's going on. And this turns out to be surprisingly useful. If you start with just pretend they make sense, 0 over 1 and 1 over 0, and you start adding things in, they stay in increasing order. They're always in least terms, and every positive fraction shows up. So like, here's the list once you do it a couple times. So I'm starting with 0 over 1 and 1 over 0, and then I add them according to this rule, and I'm going to get 1 over 1. And then after that, I'm going to take these two, and I'm going to add them together and get 1/2. I'm going to take these two and add them together and get 2 over 1. And then fill in 1/3, 2/3, 3/4, etc. Does the rule make sense? And the claim is that as you keep doing this, you're actually going to get every positive rational. And you're going to get them.
When you change between equivalent representations, don't you get a problem in the previous definition?
Sorry, say that again.
So like say instead of 2 by 3 you write say 4 by 6. So like don't you get any problems?
Yes, if you started with something that was not reduced, then you would get something weird. But I'm starting with 0, 1, and 1, 0. And I'm saying that if you start with those and then start inserting terms, those always stay in least terms. Yeah, so if you start with A and B not in lowest terms, and then you add it to C over D, yeah, you can get weird things that show up. But in this particular case, where you just start at the two extremes, 0 and infinity, and you start inserting things, every reduced fraction shows up. And there's a little proof of that with using matrices that I'm not going to go into because I want to get to. Sorry? Okay, I'm not hearing a question. All right.
Someone was accidentally unmuted.
Okay. So the main thing that I want to think about that. So this is sort of an interesting operation where you just go ahead and you insert fractions like this. This means that you never have to actually factor integers in order to produce the rationals in lowest terms. This is actually used in certain computer programs for getting arbitrary rationals, iterating through arbitrary rationals without having to do any kind of complicated factorization involving primes. And in fact, this is very closely related to something called the fairy tiling of the hyperbolic plane that you can end up thinking about. This is 0 and infinity. And when you add those two together, you get 1. When you add those 0 and 1 together, you get a half. When you add a half and 1 together, you get sort of go through and you can get, there's a bit of hyperbolic geometry in the background that sort of connects up with these things. And I'm concerned a little bit about time. I can see a lot of things in the chat that are popping up. Simon, can you monitor the chat and let me know if there's stuff that's going on there that we should talk about?
Sure.
Yeah, because I can't see it on my full screen with the pictures on the side. Okay. I want to get to the main topic. So let me go ahead and continue on and do continued fractions. So continued fractions are just where you do like Euclidean algorithm repeatedly. Like if you have an improper fraction, you can make it into 3 plus 4/7. You could end up flipping over the 4/7 and making it 7/4 in the denominator. And then you could make that into a proper fraction. And then you could flip that over and then make that a proper fraction. And you end up stopping and getting something like this. So I think many of you have probably seen continued fractions of this type as sort of a nice high school topic for getting something that you can get interesting math without doing a whole lot of complicated things. But there's more general ways that you can talk about continued fractions. This way, every positive real could show up this way. If you do it with something that's irrational, then it stops. If you do it with an irrational, it keeps going forever. You can do it for pi. You end up getting stuff like this. Was it, Caden, was there a question? No. Okay. And in fact, when you look at the theory of continued fractions, these end up being the best rational approximations to the real number. And so like 3 is the best integer approximation to pi. 3 plus 1/7, 22/7 is the next best rational approximation. And then if you keep going, you'll get better and better. But it looks a little random. It's not really clear what's going on. If you do it for E, again, not really clear what's going on. But now there's more general ones where you could just say, take some random number, complex number over a complex number, plus a complex number over a complex number, plus a complex number over a complex number. And you could consider this, and you could say, does this make sense? And to talk about whether it makes sense, whenever we have an infinite process, we usually talk about doing a convergence, a limit of finite answers. And so we'd say, okay, just look at this first fraction, and then look at the first 4 numbers, and then these. And then if those real numbers, those complex numbers are converging, then we'll say that that is the answer. And if it doesn't converge, we'll say that there is no answer. All right. I really get unnerved on Zoom when I can't see people's faces. Does this make sense? Yes. Okay. All right. So if you have a repeated pattern, this ends up leading to quadratic equations. But let me do some examples. So like, here's a different continued fraction for pi. And this one's actually pretty nice. It's got a little bit of weirdness at the beginning where it's just like 4/1 plus 1 squared over 2 plus 3 squared over 2 plus 5 squared over 2 plus 7 squared over 2 plus ... And then there it's just continuing on. Odd numbers squared over 2 plus. And it's nice and pretty. Here's one for E that's also really nice. It's got a little bit of strangeness at the beginning. E equals 2 plus 2 over 2 plus 3 over 3 plus 4 over 4 plus 5 over 5 plus 6 over 6. Okay, that's fine. Those are sort of nice things, but they're a little bit weird. What gets kind of interesting is when you do this with variables. You can actually write down a continued fraction that works for anything for the arctangent function. That if you plug in any number that if you want to find arctangent of x, you can plug in that value for x, calculate the sort of partial things with this continued fraction, and they will converge to arctangent of x. Or here's one for tangent. In fact, there's a general theorem that says that if you take a power series that has a nice pattern to any of our nice special functions like e and sine and cosine and arcsine and arctangent, any of the ones that have these nice power series expansions that we end up looking at, they also have nice continued fractions. And there's a way to convert between the two, which is not really the point of this talk, because I want to talk about something that's a little bit more basic about square roots and connect up to something called the Mandelbrot set. So let's keep going. But this is sort of strange that there's these things where you can do it with arbitrary functions. And so now let me show you one that's even more bizarre. Nice power series means nice continued fraction. Suppose you looked at one like this. This one, I have x over 1 plus x to the 5th over 1 plus x to the 10th over 1 plus x to the 15th over 1. I'm just going up by powers of 5. And then I'm going to do another one, but I'm going to start with the 5th root. And then once I've written down those two numbers, there's actually a claim that Ramanujan made that there's a relationship between the two, that the 5th power of v is equal to u times this crazy fraction in terms of u. And so for those of you that haven't heard the story of Ramanujan, Ramanujan grew up in the south part of India, near Madras. And he had a math education, but he quickly outstripped the education that was available to him locally. He was proving all kinds of strange things. And his professors were writing letters. This is around beginning part of the 1900s, around 1910. And they started writing letters saying, there's this student, he's proving all these great things. We want him to come and visit your university and be trained as a mathematician. And in his letters where he was mentioning all the stuff that he was claiming to prove, he had some stuff that raised eyebrows, one of which was that he said that 1 plus 2 plus 3 ... equals -1/12. And so many mathematicians looking at that would say, this is nonsense and this person is a crank. But then he also said things like this. This was in one of Ramanujan's letters. And eventually this letter got to Hardy in England at Cambridge. And Hardy looked at this and he said, a single look at this would show that it's enough to show that they could only have been written down by a mathematician of the highest class. They must be true, because if they were not true, no one would have had the imagination to invent them. And in fact, this is true. It is something that's some very deep mathematics. And in fact, there's even a way to make sense of the one where 1 plus 2 plus 3 ... equals -1/12. That one also makes sense once you get a little bit more background, which is not the part of this talk. So now let's get to the thing that I really want to talk about, which is continued radicals. But at this point, hopefully you're sort of familiar with the kinds of things that I want to talk about. It's like, okay, does it make sense if we start taking the radical of the radical of the radical, the square root of 2 plus square root of 2 plus square root of 2 nested like this? Does that limit make sense? What's x? Well, if it's going to be anything, we're going to do convergence based on chopping off the sequence. If it's going to be anything, it's got to be, the only possibility is where x is equal to square root of 2 plus x, because it's got this sort of self-similarity going on. And because of the self-similarity, then we can say, great, go ahead and square it to find the answers, move it all to one side, factor it. It's like, okay, if this makes sense, it's either going to be 2 or it's going to be -2. These are the only two possible answers. -2 doesn't make sense for similar reasons. And so the only possible answer is 2. Now the hard work begins. You look at the approximations, they're increasing. They're getting arbitrarily close to 2, and done. So infinite square roots of 2 plus square root of 2 plus square root of 2 actually limits to 2. That sounds sort of believable, but now let's try and push things and see what happens if we change things around a little bit. So what if I did something like this, where I changed the 2 to an A? Well, once again, we could say, all right, well, if this makes any sense, the only possibility would be where A is equal to square root of A plus X. That implies that x squared minus x plus minus A equals 0. Quadratic formula, we only get those two possible answers. The only possible answer is with the plus sign. If you do it with square roots of 1 plus square root of 1, you end up getting the golden ratio. And if you do it with square root of 2, then you end up getting 2. Okay, so that's okay, but now I want to push it a little bit further. And what I want to do is I want to pick some signs. And so what I want to do is I've put plus or minus signs, but what I want to do is I want to say, okay, what if I was looking at square root of 2 plus square root of 2 minus square root of 2 plus square root of 2 minus square root of 2, some sort of sequence of signs. I fixed the signs ahead of time. And then I want to say, okay, look at the approximations. What do they limit to? And so like imagine that the signs went plus, minus, minus, just infinitely off, just repeats. Then you could end up solving this, and the answer ends up being 2 cosine pi over 7. And hopefully that's a little bit of a surprise. Is it clear what I'm doing? At least the couple people I'm seeing are not nodding. So is it clear what I'm doing? So I'm taking, so with this case, I'm doing, okay, let's put a plus out front, and I'm going to do square root of 2 minus square root of 2 minus square root of 2 plus, minus, minus, plus, minus, minus. And I'm going to chop it off here, and then I'm going to chop it off here, chop it off here, chop it off there. And I can actually calculate those real numbers. And then seeing what they limit to, and they'll end up limiting to 2 cosine pi over 7. Okay. Let me try another one. So like there it actually is written out.
There's a question in the chat. Can you get everything between 1 and 2 for a suitable choice of signs?
That's an excellent question, and that's what's coming up in the next slides. Okay. So here it is with the particular choice of signs that give you 2 cosine pi over 7. If you just strictly alternate, then you get 2 cosine pi over 5. What's going on? And let's actually now do exactly, this is the main theorem. Let's do exactly what was in the chat. So go ahead and fix a set of signs. And I'm putting a sign in the very front as well. And so, I'm putting an epsilon 0. So the question from the chat, I'm actually going to get, so before we start going through this list, let's go ahead. So I've got an epsilon that gives me a sign. I've got a first sign, a 0th sign, a first sign, etc. No matter how I choose the signs, this always will converge to a real number. That should already be slightly surprising, but also kind of believable. But then let's go to the next statement. It converges to a real number between -2 and 2. That's actually not too hard to convince yourself of, because you could just say, if you have something down here that ends up giving me something between -2 and 2, then when I add 2, it's going to be between 0 and 4. When I take the square root, it's going to be somewhere between -2 and between 0 and 2, but then I put a sign on it, and so it's somewhere between -2 and 2. And so there's sort of a nice property of being preserved as you start iterating through this. Now to the question from the chat. Oh, no, not quite. If you have repeated signs, if your signs eventually repeat, you're going to get 2 cosine of rational multiple of pi. That one should sound a little bit more surprising, but now let's get to the one that was in the chat. Every number between -2 and 2 is the answer for some set of signs. Okay. Every number between -2 and 2 is the answer for at most 2 sets of signs. You get 2 sets of signs if and only if it's a rational number with a power of 2 in the denominator. 2 cosine A times pi, where A is some number with z adjoining 1/2, which is going to be some integer over a power of 2. All right. Everybody with me so far? I haven't given you the proofs. We'll talk about the proofs in a second. But the idea here is that this actually works really nicely, that you can get, that if you have repeated sign patterns, you end up getting nice numbers involving cosine. If you pick your signs appropriately, you can get anything between -2 and 2. But then the one that hopefully will surprise you slightly is that everything we're doing really matters that we're using a 2 under the radical. That if I replace the 2's with 3's, all of this breaks down. If I replace the 2's with 1's, all of this breaks down. Something else happens, something very pretty, but the kinds of claims that we're making here is really going to break down. Okay. So let me go ahead and move on to a slightly different topic, which will converge back in a second. There are these things called fractals, which you've probably heard of. They're things that show up that have some sort of self-similarity. The picture that I've got here is taken from Wikipedia. It's actually it looks like a picture of a fern, but it's actually produced by just 3 linear transformations. And so the way this picture is produced, just to sort of highlight it, is start with a solid black rectangle, and then write down the linear transformation that takes this solid black rectangle and maps it to this light blue rectangle, slightly parallelogram, slightly tipped. A second linear transformation that moves it down to this red parallelogram, a third transformation that moves it down to this dark blue parallelogram, and then take the union of those. So imagine that you had an initial big black rectangle, oops, and then you applied 3 linear transformations to that big black rectangle, and you got three smaller parallelograms. Then take the union of those 3 small parallelograms and apply each of the 3 transformations to end up with 9 different, even smaller parallelograms. And then take the union of all 9 of those and then apply each of the 3 linear transformations to end up getting 27 even smaller parallelograms. And if you do that repeatedly, you end up getting this picture of a fern. And so this was something that people were doing. Benoit Mandelbrot back in the 70s was doing this. And they were applying these linear transformations, and they were doing like Thurston did and just said, what happens if we do this repeatedly? And they ended up doing this on very slow computers. They were printing it out on dot matrix printers. And so they said, okay, do this 10 times so that you end up with 3 to the 10 kinds of things. And what they got from the dot matrix printer was something that looked like a fern. And at first they thought somebody was playing a practical joke on them because it's like, okay, wait, how did this show up? But then you start investigating. It's like, yeah, there's something secretly fractal about nature. Nature is sort of applying simple linear transformations repeatedly and getting the kinds of shapes that you see in clouds and mountains and trees and things like that. And if you've ever looked at, when you look at films that have like artificial landscapes that fly over planets, they're produced using iterated linear transformations and a little bit of Brownian motion. They're using a lot of mathematics in the background that in the 70s and 80s, people started realizing, oh yeah, there's a really nice fractal nature to a lot of the stuff that we see around us. So how is this connected up to other things? Well, I want to go back to Thurston. And I want to go back to imagining that I had something like a calculator. And what I want to do is I want to take, on normal keyboards, you've got this sort of list of function keys at the top, sort of F1 up to F11 or 12. What I want to do is I want to imagine that I've got an infinite keyboard where I've got an F sub C key that it's sort of pre-programmed so that if I have a number on the screen, a complex number Z, and I hit the F sub C key, that it ends up changing that number into Z squared plus C. Okay? And what I want to do is I want to type a number on the screen, and then I want to do the Thurston thing. And I want to see what happens. And so the Mandelbrot set is something where it's like you pick your favorite complex number C, you hit the F sub C key starting at 0, and you see whether or not it heads off to infinity. Okay? So the thing that I want to describe here about iterating these kinds of just square and add a number. So like if you plugged in, if you hit it with the F sub 2 key, let's just do that orally for a second. So if I started at 0 and I hit F sub 2, it would square 0 and add 2, and I would be at 2. And then if I hit it again, it would square 2 and add 2. And so I'd be at 4 plus 6. And then it would square 6 and add 2. I'd be at 38. And then it would square 38 and add 2. And it'd be some other big number. But you can see that these numbers are just growing. And they're going to easily head off to infinity. But it could be that if I write down that if I pick different keys, 0 might actually stay around the origin and not go too far away. And so the Mandelbrot set is exactly what it looks like where it stays bounded. And there's a different way where you say, so I want to describe something that involves two complex numbers. There's like the starting number and there's the key. So I put a number on the screen, I pick a key, and then I just hit the key repeatedly, and I see what happens. And the only thing I'm going to pay attention to is whether it heads to infinity or not. If it gets big enough, then it's going to head off to infinity and nothing's going to stop it. If it stays around for a long time, then we're going to draw it. And then because this is two complex numbers, this is something in four-dimensional space, which is hard to see. And so we're going to look at slices of it. And so I could either say I'm always starting at 0, and then I'm going to just say what happens with the different keys. Or I could say that I'm looking at a particular key, but I'm going to vary the starting points. And these are called the Mandelbrot set and Julia sets. No idea whether people are understanding. But does this kind of make sense? I mean, we're really getting into the Thurston thing. It's like pick a number, put it on the screen, pick a key that's doing something simple. It's just squaring and adding a particular number, and do it repeatedly, see what happens. And so let's go ahead and do some images. So here is a Julia set. Okay. This is the Julia set for the particular complex number C equals blah, 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 blah. So imagine that I had the F sub C key. If I start at one of the purple points, this is in the complex plane. If I start at one of the purple points and I hit the F sub C key repeatedly, it will bounce around between the purple points, but it will never end up going off to infinity. If I pick a white dot like this, and I keep hitting the key repeatedly, it might bounce around for a bit, but eventually it's going to head off to infinity. And so this is sort of telling me which starting points stay around, which starting points go off to infinity. Okay? I've fixed the key, I'm varying the start point. This is what happens. Nice source of fractals. The Mandelbrot set is the other way around, where I'm fixing that I'm starting at 0, and then I'm changing the key. And so here's the Mandelbrot set. And this is the point 0. This is the point -1. This is the point -2.
There's a question, what is the area of that set?
I have no idea what the area is. I'm sure somebody's tried to calculate it. But actually, this is a nice perfect circle. You can see sort of nice bits. This is a nice cardioid here. If we said the F2 key, if it was starting out way over here, it just heads off to infinity. If you start out with any positive key, it just heads off to infinity. Things over here just start moving around. Does the distinction between Mandelbrot and Julia make sense? We've got two numbers, starting number, and then the key we're going to hit repeatedly. And then if I always start at 0, and then I hit a key repeatedly, this tells me whether that particular key iterated at 0 goes off to infinity or not. Black means it stays around. Out here tells me it's going off to infinity. Let me actually show you some other. It's got some nice self-similarity. You can see that this thing here at the top looks like the little bug over there. These look like smaller copies. And in fact, it's fun to sort of zoom around. If you zoom in to this area right here, it looks like this. If you zoom in a little bit more, you start seeing some spirally stuff. If you zoom in a little bit more, okay, that's kind of interesting. Let's look over there. Oh, and if you go deep down into it, there's another copy of, looks kind of like the Mandelbrot set. It's really sort of there's online viewers where you can fly around the Mandelbrot set. It's sort of interesting. But let's go ahead and.
What exactly does all the color represent? Like,
good question. So the color. So one thing I was telling you is that if you ever get past a certain size, it's going to head off to infinity. And so the way that they give the colors is they say, take a particular starting point, start at 0, hit the key. It might bounce around for a little bit, but at some point it might head past the barrier. And what the color is indicating is how many times you had to hit the key before you pass the barrier. And so then you can sort of see what's happening. Then it sort of gives you nice changes as you slightly move from thing to thing. I think they've smoothed it out as well. But yeah, it's basically saying how many times do you have to hit the key before you can guarantee that you're heading off to infinity. And so everything that's actually in the Mandelbrot set is actually staying black. But this is sort of a colors that are put on the things that are outside the Mandelbrot set, telling you how long you have to hit the key before you can be guaranteed that you're heading off to infinity. Okay. But now I want to tie this back into some other stuff. So there's the one down at the very bottom that looks kind of like the original Mandelbrot set. It's got self-similarity, but it's sort of hidden. But now I want to connect this up to some other things. We had cosines showing up a second ago. Let's go ahead and go back to cosines. Most of you know the double angle formula for cosines. Cosine 2 theta equals 2 cosine squared theta minus 1. But I want to rewrite this a little bit. I want to rewrite this way. I want to rewrite it. I want to put the 1 on the other side. I want to double things. And so I'm writing it as 2 plus 2 cosine 2 theta is equal to 2 cosine theta squared. Okay. Partly why I want to do that is I want to then go ahead and fix theta, and I want to let x naught be 2 cosine theta. Then what this formula, this double angle formula tells me is that x1, so x0 equals that, equals that, equals that. I'm just doubling the angles. And if I do that, then the double angle formula tells me that these numbers, x0, x1, x2, are related by this formula. Right? Because like this is x0, this is x1. This is, if I double the angles, then if I put 2 theta, and then this would be x1, this would be x2. And so suddenly, from the double angle formula for cosine, you end up getting its relation to, if you look at cosine theta, cosine 2 theta, cosine 4 theta, etc., as a sequence, the sequence ends up being related by hitting the f-2 key, to use the Mandelbrot language. That I can get xi plus 1 by taking xi squared and subtracting 2. All right, all I've done is I've said, okay, take something like this. Then I end up with the sequence of numbers that satisfy this pattern. But then if I solve for xi plus 1 equals that, which is the same as saying in our Mandelbrot language, hit the f-2 key. And so the xi's are actually what you get if you start with the number x naught and you just hit the f-2 key repeatedly. If you take a number that's equal to 2 cosine theta and you hit the f-2 key, you get fx1. If you hit it again, you'll get fx2, x3, x4, x5. You'll get a sequence of numbers. All right. Somehow there's this connection between, and then, so this map, the f-2 key, let's go back and see where -2 was in the Mandelbrot set. -2 was this point right there. So this was 0, this was -1, this was -2. And then the point about Julia sets is that we're talking about some shape in C2 in 4-dimensional space. The Mandelbrot set is sort of saying what happens at 0 with the different keys. But then for every point in the Mandelbrot set, there's a Julia set in the other coordinate saying something like this. Right? Saying that if I fix on a particular key, like if I said I'm going to fix on the -1 key, sitting above that in the other complex direction, there would be a Julia set. Basically, what you should be thinking of is that there's some 4-dimensional swirly shape that kind of looks like a bug. And if you slice it where the first coordinate is the complex number 0, you end up seeing this picture. But at any particular point, you could slice it in the second complex direction, and you would end up seeing something like this picture. This should be stretching your imagination a little bit. We usually don't think about shapes in 4-dimensional space, but there's some sort of swirly thing in 4-dimensional space that if you slice it at the coordinate plane equal to 0, you see this. And if you slice it vertically, you see this. This is what happens when you slice specifically vertically at this point. Okay, so let's go back.
Is there any reason why we chose that point?
So the f-2 key is the very, very tip of the Mandelbrot set.
Is there a specific reason why we chose that point specifically for C in the Julia set?
No, it was just to give you an example that was sort of got an interesting one. It also happened to be a picture that was on Wikipedia that I could just grab.
Okay.
Yeah. And basically, one thing that I should say is that if you go back and you look at the Julia set for something on the inside, then you get something that looks like it's connected like this. But if you pick a point on the outside, then what the Julia set would look like, it would basically look like a Cantor set. It would look like dust. It's sort of all spread out. But it turns out that there are 2 places where the Julia set is really, really nice. If you think about this point 0, the doubling map is just the squaring map. And so if you think about what squaring does to complex numbers, if you take a complex number that's inside the unit circle and you square it repeatedly, it's just going to go zipping down to the origin. It's going to stay bounded. In fact, if it's on the unit circle, it's just going to spin around. It's going to stay bounded. But if you have something that's outside the unit circle and you start iteratively squaring it, it's going to head off to infinity. So for this particular point, the Julia set looks like the unit disk. Okay? For crazy points, they look crazy. For points outside, they look like dust. But it turns out that the tip of the Mandelbrot set also has a nice Julia set. Let's go back. Okay, so the tip of the Mandelbrot set, the F-2 map, is the doubling map. And there are strong connections between the double angle formula for cosine, the doubling map, x squared minus 2, and its multivalued inverse, which is basically saying take plus or minus the square root of 2 plus some number. And so the iterated square roots with signs is actually very closely related to undoing the doubling map, undoing the F-2 key. And so and binary decimal expansions, the real numbers. So I haven't mentioned the Julia set for the tip for the if you pick the number -2, if you look at the F-2 key and you look at its Julia set is exactly the interval -2 to 2. And the interval -2 to 2 gets sent to itself, sort of stretched out, folded over, stretched out, folded over, stretched out, folded over. But it maps the interval -2 to 2 to itself. And it ends up being exactly the Julia set for the tip of the Mandelbrot set. And so the main theorem that I listed earlier, that the iterated square roots with 2's under the radical is closely connected to the inverse iterates of the doubling map. It ends up being related to the Julia set of the doubling map, and the map indexed by the tip of the Mandelbrot set, and it's exactly this interval -2 to 2.
There's a question. Why isn't the Julia set empty for C outside the Mandelbrot set? Wouldn't the sequence for non-zero starting point be bounded below by the sequence starting at 0?
We got to make sure and keep track of the two different numbers. If we're picking a point outside the Mandelbrot set, that's telling us the key we're using. The Julia set is determining which initial inputs stay bounded. And so just because we have a key that's on the outside, there might still be an initial input that ends up just sticking around. But they're going to be few and far between. They're going to look like a Cantor set worth of points that end up mapping among themselves. But even with a key outside, you might have special starting points that still stay around.
And there's another question. Are the Julia sets of numbers inside the Mandelbrot set actually connected, or do they just look that way?
That's deep research, and I believe that if it's strictly inside, people have proven it for ones that are sort of like little pinch points. I haven't looked at the literature recently, but that's something that's got a lot of technicalities in order to try and prove it. But it's definitely been a conjecture back when I was originally looking at this, that if you're inside the closed Mandelbrot set, that you should have a path connected Julia set. But it ends up involving a certain amount of technicalities when you're near the boundary. All right. This is sort of giving us a sense about when I said the main theorem that it really depended on 2. When I was doing the iterated square root of 2 plus or minus square root of 2 plus or minus square root of 2, when I said if you change 2, you get something else. What ends up happening is that if you change the 2 to a different number, is that when you do those iterated square roots, basically your numbers end up converging to points in the Julia set. That when you start taking the square root of 3 plus or minus the square root of 3 plus or minus the square root of 3, you end up getting answers that become complex, not staying in the reals, and they end up approaching something in the Julia set for -3, which is some crazy Cantor set-like set of points. And so you can get theorems for other numbers, they're just not as nicely stated. Okay? And so like if I put this number under the radical, if I said take the square root of C plus or minus the square root of c plus or minus the square root of c. And of course, now square plus or minus is a little bit weird because we're talking about complex numbers. It's just like pick one of the square roots, et cetera, et cetera, et cetera. If I started doing iterated square roots of c plus square root of c plus square root of c with plus or minus signs, it would end up approaching one of the purple points rather than approaching things between -2 and 2. And let me now go back because I've got one last slide. So there's these connections between doubling maps for cosine, the doubling map x squared go -2, iterated square roots. If you replace 2 with another point, you get convergence to an arbitrary point in its Julia's set. But now I want to sort of bring this back to Ramanujan, because Ramanujan not only investigated all kinds of things with continued fractions, but he also investigated some continued radicals and actually wrote this in one of his notebooks. He wrote 2 cosine theta is equal to, and then you can see this is very related to the stuff we were just talking about. That you could say, oh yeah, 2 cosine theta, I could rewrite that as the square root of 2 plus 2 cosine 2 theta. And then I could rewrite the 2 cosine 2 theta as the next thing. And then he says, but then the person who was editing the notebooks in the 90s, Bruce Barrett, said, you know, we're going to state this entry like Ramanujan records it. But as we can see, it's only valid for theta equals 0. And we suggest to the readers that they attempt to develop more thoroughly a theory of infinite radicals. And I took that as a challenge. And so I went through and I started playing around with this. And in fact, all you need to do is replace his plus signs with plus minus signs. And what he said is perfectly valid, that for 2 cosine theta, there is a particular sequence of pluses and minuses where this all works. And it's connected up to the Mandelbrot set, and it's connected up to all kinds of pretty things, and a whole bunch of really interesting mathematics. And that's what I've got. All right. Thank you for your attention.
Okay, thanks for a great talk. So are there any more questions?
Yeah, so I appreciate all the different questions during the talk. Hopefully that slowed it down enough so that things made some sense. But I do think that there's a lot of stuff here that's sort of interesting and really accessible. It's surprising to me that the double angle formula for cosine ends up connecting up to nested square roots, connected up to Mandelbrot set. Go and play with it. It's really kind of fun.
Where could I find like a proof of the theorem you stated earlier, where if you have a nested list of square roots with like some permuting signs, that you get something of the form cos of a pi?
Oh, yeah. So what I didn't do is I didn't talk to you about the proofs, but basically there's a way of, if you take theta and you write it as a binary decimal times pi, if you take the theta that's showing up, if you think of it as a times pi and you write it as a binary decimal, there's a way of actually, yeah, let's go back. So suppose I had some number x and I wanted this to appear as a nested square root. Then what this is telling me is I could go ahead and start applying. I could find these other numbers by just hitting the f-2 key. And as I hit the f-2 key, what I can do is I can just say, okay, well, maybe x0 was a positive number, somewhere between 0 and 2. And then when I hit the key, maybe it becomes a negative number. That actually tells me that the second sign has to be negative. And then when I hit it again and I look at the sign of x2, that tells me the sign that I have to have after that. And so as I start just hitting the f-2 key and recording the signs, that ends up being the sequence of signs that you need in order to get the sequence to converge to that original x0. That you can actually just produce them. How do you end up getting 2 possible sets of signs? Well, maybe you ended up landing at 0. And if you end up landing at 0, then the sign in front of that doesn't matter. But then after that, it'll have a particular set of signs. But this gets to the connection between if you wanted to do this all at once, where you could see the set of signs from the original number x naught, take x naught, write it as 2 cosine theta, factor out a pi, and then write the thing in front as a binary decimal. You can actually predict the signs from whether it's a 0 or a 1 in that binary decimal. And so if you have something that ends up being a rational multiple of pi, it'll have a repeating binary decimal, which will end up giving you a repeating set of signs. Does that make some sense?
It does. Thank you.
Okay, yeah. Yeah, and so you can actually connect up the binary representation of the theta once you've factored out the pi, the set of signs that are showing up, and that's why you end up getting rationals in binary. And you can also see why the thing about when you have 2 sets of signs, that because the iterating doubling gives you something that lands at 0. Okay. Any other questions?
Do you have any recommendations for where we can further read up on things you've talked about today?
Yeah. Well, let's see. I'm happy to make my slides available. I have some notes written up, but more importantly than that, there's various. Yeah, let me say it this way. So this was something that I did when I was playing around with reading Ramanujan's notebooks back in the late 90s, early 2000s. Like I said, I've never written it up as a formal article, but I do have some notes. But if you look in the literature, if you just search online, there are lots of articles that have appeared in the last 25 years about infant square roots, nested square roots. And there's a lot of this stuff that's shown up. I don't think the connection to the Mandelbrot set has really been brought out, but there are quite a few different papers, maybe half a dozen to a dozen, that have been written about iterated square roots with 2's under the square root, nested square roots. And so you can find a certain amount of this in the literature. But yeah, if you want to know more, I don't know, send me an email. I can and then talk to you about it. Okay.
Thank you.
Okay, thanks. Anything else?
Okay, so if there are no more questions, then yeah, thanks again for a great talk, and then we'll move on to the next part of class. So, bye.
All right, thanks.